Welcome to the Explainer. Today, we're going to break down a statistical method that could seriously save you millions and help you make way smarter decisions. It's called hypothesis testing, and trust me, by the end of this, you'll see how it can be your secret weapon for turning data into real, decisive action.
All right, let's jump right in with a super common situation. Picture this. You're in charge of quality control. Your machines, they're supposed to be filling cereal boxes to exactly 300 grams. Now, stopping the production line costs a fortune, but so does shipping underweight boxes. You can't check every single one, right? So you grab a small sample. How on earth do you make a potentially multi-million-dollar decision based on just a handful of boxes? And that is the classic manager's dilemma, isn't it? Making these huge calls with just a tiny piece of the picture. Guesswork is just too risky, and your gut feeling, well, it's not always reliable. What we really need is a solid, structured way to deal with all this uncertainty. A way to go from just hoping we're right to having real, data-driven confidence. And that, right there, is exactly where hypothesis testing comes in. It is a formal, structured method for using a small sample to make a really big decision. It doesn't matter if you're looking at a production run, a new market, or a sales strategy. It's all about making that smart call and being able to back it up with data. Okay, so before we get into the nuts and bolts of how to do it, it's super important to get the logic behind it. And the fundamental idea is actually something we all get, because it's basically borrowed straight from a courtroom trial. So in statistics, just like in court, we start by assuming innocence. We call this the null hypothesis, or H0. We just assume everything's working as expected. The machine is filling boxes correctly, that new ad campaign isn't doing anything special, you get the idea. The burden of proof is completely on our data, our sample, to show beyond reasonable doubt that our initial assumption is wrong. The claim we're actually trying to prove, that the machine is faulty, that's our alternative hypothesis. Now, you'll see some of the text here is from one of our Spanish sources, but the idea it shows is totally universal. See, in any decision like this, there are two ways you can mess up. A type 1 error is like convicting an innocent person. You stop a perfectly good production line. A type 2 error? That's letting the guilty go free. You end up shipping a bad batch of products. Hypothesis testing is all about consciously trying to balance these two risks. So the big question is, how do we actually put this awesome logic to work? How do we get from a business problem to a clear statistical verdict? Well, it's not magic. It's actually a really clear 5-step process that we can apply directly to our cereal box problem. We're going to walk through each of these steps one by one. Think of this framework as your roadmap. It's what ensures you've covered all your bases and that your final conclusion is totally sound and, maybe more importantly, defensible to your boss. So step 1 is really just about picking the right statistical model for the job. Let's skip ahead to the real meat of it. Step 2, stating our hypotheses. Our null hypothesis, H0, is that everything is fine and dandy. The average box weight is 300 grams. The alternative, H1, is that nope, there's a problem. The average is not 300 grams. Okay, on to step 3. And again, don't worry about the Spanish text here. Just focus on that formula. We use this to calculate our test statistic, which is just a single number that basically summarizes all of our evidence. You can think of it like a score that tells us how surprising our sample result really is. The further that number is from 0, the more surprising the result. So for our sample of cereal boxes, we crunch the numbers and we get a z-value of 0.08. Okay, so we have a number. It's a really small number. But what does it mean? Is it small enough to be considered innocent, or is it so far out there that it proves guilt? On its own, this number is pretty meaningless. We need some context. And that is exactly what step 4 is for. This graph is fantastic because it shows our decision rule visually. Before we even looked at our evidence, we drew a line in the sand. That huge area in the middle, that's our region of acceptance. If our evidence lands there, we're going to stick with our innocent assumption. But those little shaded areas on the ends, in the tails, those are the regions of rejection. If our evidence falls in there, it's just so unusual, so far from what we expected, that we have no choice but to reject our initial assumption. So how do we decide where to draw those lines? Well, we choose something called a significance level, and typically it's set at 5%. This is basically our risk tolerance. We're saying, you know what, I'm okay with having a 5% chance of making a mistake and stopping a good production line. And that 5% risk level translates to B specific values on the graph, -1.96 and +1.96. If our evidence falls outside those boundaries, it's strong enough evidence for us to take action. All right, let's get to the good part. Step 5, the verdict. Remember our test statistic? It was 0.08. So where does that fall on our map? Well, as you can see, it's smack dab in the middle. It's squarely in that big white region of acceptance. It's nowhere near those critical rejection zones out in the tails. So our conclusion is crystal clear. The data has spoken. We simply do not have enough evidence to reject the null hypothesis. Let's put that in plain English. Based on our sample, there's no good reason to think the production line is faulty. We can let it keep running with confidence. And just like that, we made a major business decision using statistics.
Okay, so that was for a single production line. Pretty cool, right? Now, let's take that same exact logic and apply it to another super common business problem, comparing two different groups. This could be anything: 2 sales teams, 2 ad campaigns, 2 suppliers, you name it. Let's say you use 2 different external companies for your sales force. You need to know if they both have the same level of product knowledge. So you give a test to a sample of salespeople from each company. How do you decide if there is a real difference between them? So here's the data we got back. We tested 10 people from each company. Now, just looking at it, company 2 seems to be doing better, right? They've got an average score of 92.4 compared to 83.3. But is that difference big enough to matter? Or could it just be random chance, based on the specific people we happen to test? You guessed it, we're going to run the same 5-step process. The core logic is exactly the same. We just use a slightly different formula back in step 3 because now we're comparing 2 groups. This gives us something called a t-statistic. And in this case, our t-statistic comes out to -1.65. So let's go back to our decision map. For this kind of test, our 5% significance level gives us critical boundaries at -2.10 and +2.10. Our result was -1.65, so it falls comfortably right there between those lines, smack in the middle of the acceptance region. So what does this mean for you, the manager? Well, even though Company 2's scores looked higher on paper, the difference isn't statistically significant. That's just a fancy way of saying we can't be sure it's a real difference. It could just be random noise in the data. So based on this test, we can't conclude that one team is actually more knowledgeable than the other.
And this really gets to the heart of it. This is the real power of hypothesis testing. It gives you this clear, objective framework to work with. It lets you actually quantify your uncertainty and make decisions you can defend with evidence, not just a gut feeling or what a number happens to look like on a spreadsheet. All right, so let's recap the game plan here. First, always start by assuming nothing has changed. That's your null hypothesis. Second, let your data make its case. Let it provide the evidence to challenge that assumption. Third, always know what your risks are of making the wrong call. And finally, stick to that 5-step process. It's your reliable guide for turning that messy uncertainty into confident, data-backed decisions.
And that brings us to the final and probably most important question. What's a key assumption in your work, in your business, that you could finally put to the test? Is that new marketing campaign you launched actually working? Is one of your suppliers truly better than the other? The power to stop guessing and start knowing is right here. So, what are you going to test first?